Hi students, today in this video we are going to discuss about carrier transport phenomena. So as we know, the charge carriers in the semiconductors can be electrons and holes. Electrons are free to move in the conduction band, holes are free to move in the valence band. So when you will apply an external electric field to the semiconductor, as we know F is equal to QE, so the charge and multiplied with the applied electric field. So we know if it is positive, the Q is positive, then the the positive charge will move in the direction of applied field, because we said mass into acceleration is equal to Q times E, right? So if Q is considered to be positive, then you can see your acceleration will be along the direction, okay, will be along the direction of applied electric field, right? And if I'll take like MA is equal to minus QE, considering electron or negative charge. So here this minus Q we consider for electron, so we consider to be negative. So then you can see actually A is here proportional to minus E. So here you can see acceleration will be opposite to that of the applied electric field, the applied electric field, okay, applied field, okay. So this is what we said. So now carrier transport phenomena is nothing but the movement of the charge carriers, okay, and this movement of the charge carriers actually will generate current. So this is what we are going to discuss today in this video, okay. So what we know, the net flow of electrons and holes in a semiconductor actually generate currents, right? And this process by which these charged particles or charge carriers move is called transport. So if I will write like what is transport, what I will say, it is the process, okay. um, we can write the process by which the charge carriers in the semiconductor, we are talking about semiconductor, the charge carriers, okay, move, okay. This is called the transport, okay. So now what is the mechanism of transport, how the electrons will actually move or the holes will move in their respective bands, like in electrons in conduction band and holes in the valence band. So the mechanism, if you will see the mechanism, we can actually classify the mechanism in two types, okay. Two types of mechanisms we can discuss. One we will call as drift, the other we will call as diffusion. There is a third mechanism also responsible for the movement of the charge carriers, which can consider to be temperature gradient, okay. So temperature gradient, difference in temperature, okay. So that is thermal non-equilibrium, okay. So that will also create the movement of the charge carriers from one region to the other. But in this case we are not considering the temperature gradient, we consider thermal equilibrium. So there is no temperature gradient in the semiconductor, so we are not considering it. So if you are not considering this, we have only two mechanisms left for the transport phenomena or carrier transport phenomena to describe carrier transport phenomena. So one is your drift, the other is diffusion. So here we are going to see one by one. Let us first focus on drift. What do you mean by drift, okay? So what do you mean by drift? If I'll tell you what is drift, um, let me start with, sorry, drift. What is the mechanism of drift? So we said the movement of the charge due to the external applied field, okay, electric field. So you applied external electric field and then the charge will move. And what is diffusion? Diffusion, let me tell you, the flow of charge due to the variation in concentration, or you can say the density gradients or concentration gradients. There is, in different region the concentration of electrons and holes will be different, okay. So then the charge carrier should move from higher concentration to lower concentration, which is known, the process of diffusion. So we'll start with drift or carrier drift. So what will happen here, in this case we are applying an electric field to a semiconductor, applied field to a semiconductor, which will produce which will produce a force on the electrons and holes, as I told you, F is equal to QE, so that they will experience a net acceleration. That is what I showed you, okay, and net movement, okay. So what will happen here? So when these electrons will actually move, okay, when they will move actually, when provided there are available energy state in the conduction and valence band, okay, then only it will move. What do you mean by this? Suppose as we said, this is our conduction band and this is our valence band, okay, this is our valence band. So when you said the holes will move, holes are nothing but the vacated electrons, right? So these are the vacated electrons. So these holes will move, okay, in the valence band, okay, only if, there are available states here, okay, there are available states. There must be some vacated places, like, for electronic states or vacated spaces here, okay, for the holes to move, right? Then only it will, drift. Same here in the conduction band also. When you got, electrons, there must be electronic states, available electronic states here, okay, available electronic states, so that the electron can also move from state to state, or in move from one electronic state to the other electronic state in the conduction band. So that has to be there, okay. So then only your drift or diffusion will occur, okay. So that is one thing, okay. This net movement of charge due to an electric field. So, okay, so the net movement of the charge, you can write net movement of charge due to an electric field is called drift. So this is the mechanism of drift. So what we did, we simply said F is equal to QE. So there will be a net acceleration A here, okay, which can be written as like Q by M times E. So if the charge is considered, charge and mass is considered, this ratio is considered to be constant, then this electric field, you can see, is along the direction of acceleration. If the q is positive, if q is considered to be negative, then it is opposite. So this is how, the movement of the electrons and holes can be determined, okay. So this is simple. Then what is drift current density? Okay, let us try to understand what is drift current density. Drift current density. Drift current density, okay. So what we said, at ordinary temperatures or room temperature, you can say, an intrinsic semiconductor, if you will consider, okay, will always contain some free electrons in the conduction band, because we said in room temperature few of the electrons will gain, thermal energy and will move from the valence band to the conduction band. So there will be always some free electrons in the conduction band and equal amount of holes in the valence band. So what we said here, if you will consider the conduction band and the valence band, this is of the order of 1 electron volt in semiconductor. So these electrons from the valence band here, for example, I'm just showing, few of the electrons will always be elevated from the valence band to the conduction band at room temperature, which is considered to be around 300 Kelvin. 300 Kelvin, at this temperature you will see. So you will see the electrons over here and the holes will be created here, holes will be created over here, right? So this is how we can say that the electrons and holes are created, okay, vacated state. So you got the holes over here, right? So these electrons here in the conduction band, holes in the valence band, are responsible for the process of conduction, as we said, right? So in absence of any applied electric field, if there is no further electric field given to this particular intrinsic semiconductor, so these electrons here, okay, in the conduction band and holes in the valence band here, okay, they just move randomly in random directions, okay. So random directions means there is no net current, okay, because there is no net movement of these charge carriers, no net movement of the charge carriers. This is simple. You can consider all the random velocity vectors and you just add vectorially or geometrically, then you will get net velocity is zero. So net movement of the charge carriers will be zero. So net movement of the charge carriers is zero. That means the current will also be zero. So which will lead to zero current, okay, or no current. So that is because of the random movement of the charge carriers in the conduction band and the valence band. Now if you will give some external electric field, apply some electric field, okay, then what will happen, these electrons and holes, okay, in the conduction band and valence band respectively, will be accelerated towards the opposite ends of the field, okay, if you will consider electrons, okay, and holes in the direction of the field, okay, and their velocity will now increase, okay. So if I will apply this E, and we know that just now we said F is equal to QE, I'm repeating it again, F is equal to QE. So this AF actually gives you what, that mass into acceleration, so there will be gain in velocity of these charge carriers as per the direction. Electrons will move opposite to the applied electric field, and holes will move along the direction of the applied electric field, right? So the carriers acquire an average increment in the velocity, okay. So okay, so this now what will happen, a little bit like initial tussle, because of subsequent collision with various types of obstacles, atomic nuclei, phonons, okay, etc., present in the semiconductor. So after that initial tussle, they will all gain, there will be average increment in the average increment, because initially they were all moving random. When you applied the electric field, there is a certain force directed in a particular direction, so there will be some initial tussle, which there will be interaction with the atomic nuclei, electron and all. So some amount of after some initial time or initial tussle, they will all be directed or oriented in a particular direction, okay. So now this velocity gain, or this extra velocity which is acquired by the carriers, the charge carriers, okay, in the presence of the applied electric field or the external electric field, we call it as drift velocity. So we will call it as drift velocity. So what do you mean by drift velocity? This is the average velocity gained by the charge carriers because of the applied electric field. Okay, so this is what we said, drift velocity. Okay, and we can mathematically denote it as V for velocity and D for drift. Okay, so drift velocity we will denote it. Fine. Let us now see the mathematical treatment of this drift velocity. Very simple. So now we said this drift velocity is nothing but the average increment in the velocity of the charge carriers under the application of external electric field, right? So from, if you write this thing in a mathematical form, then we can write it as what, Vd, which is the drift velocity, is directly proportional to the applied electric field. Okay, so this is what we can write. Suppose you will say, okay, for holes, let us write for holes and for electrons separately. I will just use different notations just to distinguish, okay, which one is for hole and which one is for electron. So I will write VdP, P for holes I'm writing, okay, is proportional to the applied electric field E. Okay, so you can write VdP. If this proportionality has to be substituted with equality, then you can write one proportionality constant, and I wrote it as mu p times E. Okay, so what is this VdP here? VdP here is the average drift velocity, average drift velocity of holes, average drift velocity of holes. And what is this mu p? Mu p we said is the proportionality constant or proportionality factor known as mobility. Here we are writing for hole, so we will call it as hole mobility. Yeah, whole mobility. So now what is mobility? If you will see what is mobility, okay, what is the literary meaning of mobility, what it actually gives you, okay, it decides, this mobility describes, or this decides how well a particle will move, okay, inside that semiconductor, or for a hole, how well the hole can move in the valence band of of a semiconductor, okay, when it is under the electric field. So how well a particle can move, okay, due to the electric field, that will be given by mobility, right? That will be given by mobility. So mobility describes, we can write, mobility describes how well particle, here in case when I'm saying particle, the charge carrier, okay, due to an electric field. This way we can just understand what is mobility. Okay, actually how well a particle, when I said it's actually a charge carrier, maybe electron or hole. Okay, charge carrier due to an electric field. Okay, now you got this vdp is equal to mu pe, the same way you can write for electron. So if you write it for electron, you can write v for velocity, d for drift, n for electron is equal to mu n, that is mobility of electron in the semiconductor, and electric field. So this way we can write the drift velocity of electron in the conduction band due to the applied electric field, and here vdp is the drift velocity of the holes in the valence band due to the applied electric field. So this way we can write. Okay, now next thing is, from this you can, if you want to write what is the unit of mobility, because we define mobility as a proportionality factor, which actually describes how well the charge carrier can move within the conduction band or valence band when under the application of electric field. So if you will write that unit of mobility, you can just write unit of mobility. I'm just writing um, mobility. If you want to write, this gives you what? This gives you centimeter square. Okay, as we just said, vdp is equal to mu p times e. So mu p can be written as vdp divided by e. Okay, so what is this vdp is, just writing centimeter per second. Okay, in centimeter, because the dimension is very less, so it is wise to write in centimeter. So centimeter per second you got, and this you got, this one is volt per meter actually you need to write, but here I'm using centimeter, so you can write electric field is actually v by d, so volt per meter, so v divided by sorry, this is v divided by centimeter, so it will be centimeter divided by v. Okay, so simply, I mean, divided by e, so this e is actually volt per meter inverse or volt per centimeter inverse, so that way you can write. So you got centimeter square divided by volt into second. This is volt. Okay, volt into second, so you can write that centimeter square divided by volt into second. So this is the unit actually, that is normally used for mobility. Okay, so there is a chart of mobility, you can just google it, or somewhere I will show you unit of mobility. So for different, like, materials like silicon, germanium and all, what is the electron mobility and hole mobility at a certain temperature and under the application of field. Okay, so that can be determined from this. Well, so after this, we will see what is the role of this mobility to determine the current density. That is what is important, because here we are trying to find out drift velocity and the drift current. Okay, so now if I'll write the drift current density due to the holes. Okay, let us do it for holes. Okay, first, then I will write J P for holes, and I'm writing DRF for drift. Okay, so this can be written as a rho, which is volume charge density multiplied with VDP. Okay, so rho is volume charge density and V is your drift velocity. We know volume charge density, we know that charge per unit volume. So charge per unit volume can be written as the charge is, let's say, plus E over here, and the concentration of hole we can write P, concentration of hole, right? So that gives you what? Concentration means what? Number of holes per unit volume multiplied with one charge of positive charge, electronic charge. So that gives you PE, right? So this is what we got for rho, and then we have EDP as it is, right? So which can be further written as this is EP, and for VDP directly I could have put there mu P times E, right? So this gives us E times mu P, which is mobility of holes, concentration of holes, and then the applied electric field. So this way we can write the current density, or we said the drift current density is, or can be written like this, or is dependent on these factors. One is charge. Okay, electronic charge, mu P, the mobility of holes, P, the concentration of holes, E is the applied electric field. Okay, so the drift current due to holes in is in the same direction as the applied electric field. That is what we have already discussed. Same way for electron, if you want to write for electron, we can write Jn. I'm writing n for electron and drf for the drift. We can write same way rho times v dn. So we can finally write this to be what, with a, this is minus En. We got charge of the electron minus En, concentration of electron, and this is vdn, right? Substitute minus En here, and what is this mu pe? Okay, so this mu p, we know that, for electron we just wrote vdn is proportional to what, VDN is proportional to, we got this minus E, because the it will move in the opposite direction. So VDN, you said this is minus mu n times E. So this is what you need to keep in mind, the negative sign, because it's moving in the opposite direction, and you substitute over here. So if you will substitute here minus mu n times E, okay, then you again got positive value En mu n E. This is what is your Jn drift, right? So this is what we got here. Now you see both the electrons. Now you can see the current density due to the electrons and due to the holes, they are actually moving in the same direction. You are getting both in same direction. So you can see that. So both the electrons and holes, they contribute to the drift current. So the total drift current, if you want to write, so the total drift current due to these charge carriers we can write, okay, whatever we got for hole, u e mu p, p and e, plus this is e n mu n e. So the final expression can be written as e taking out, and you got mu n times n plus mu p times p, concentration of hole, concentration of electron here, mobility of electron and mobility of hole, multiplied with this applied electric field. So this is the expression for the total current density due to drift, the mechanism of drift. Okay, so this is it, and in the next class we will see what is the effect of mobility or mobility effects, how mobility is actually affected. Okay, or mobility will be decided, or mobility is dependent on other factors. Okay, that is what we are going to say. Okay, thank you for watching.